Hi there, Advanced Hat. Welcome to your lesson for this week. This is week beginning on 1st of February. Today we'll be looking at some of the stuff we've been doing for simple harmonic motion and what you've learned from waves, putting it together, and we're going to look at what I've called advanced waves. So we're going to start off with something, a new term known as phase difference. It's on page 76 of your textbook. And the first thing is to think about is that rotational motion and wave motion are both considered cycles and have a beginning, a middle and an end. So rotational motion, beginning, goes round in circles like this, beginning, middle, end, and it just keeps going. Waves go up and down. You have a beginning, a middle and an end. So this would be, say, a beginning, that would be a middle, that would be an end. If the wave started here, that would be beginning, middle, end. So one rotation is the same as one cycle, which is 2 pi radians, and it's one wavelength. And half a rotation is half a cycle, pi radians, half a wavelength, half lambda. So one complete wave is the same as 2 pi radians, as the same as one complete rotation. Now, phase difference is the distance round the cycle is represented in radians. So how far around that cycle you are, or how far you are through the wave, can be represented as in radians. So phase difference is the separation of 2 points in a wave as a fraction of the wavelength expressed as an angle in radians. So this little diagram down here comes in handy. So if you're starting at A and going to B, then that horizontally, so the formula here is the phase difference or phase angle is a horizontal separation times the wavelength times 2 pi. So the horizontal separation there would be the distance between A and B horizontally. For C, it would be A and C horizontally, D, A and D horizontally, and E would be A and E horizontally. So if you look at A and E, for example, there to there is one complete wavelength. So the horizontal separation would be equal to the wavelength. So it would be 1 over 1 times 2 pi. So A to E is just 2 pi. A to C would be half a wavelength separation divided by the wavelength times 2 pi, which ends up being to C would be 1 pi. So this symbol here is like a capital theta. I'm pretty sure it's capital theta. It might be an omega, capital omega. I can never remember what this is called, but it's the phase difference or phase angle. And it's x, which is horizontal separation, divided by lambda times 2 pi. 2 pi comes over or goes up and becomes 2 pi x over lambda, and that is your phase difference. Next part is to look at wave energy transfer. The energy transfer by a wave is proportional to the amplitude of the wave. The greater the amplitude, the more energy transfer. This is still on page 76 of the textbook. As the amplitude is increased, then both the height and the depth of the wave is increased. So here's a normal wave. If you increase its amplitude, it doesn't just increase up the way, it increases down the way as well. So your high energy wave is actually not just double the height, it's also double the height and double the depth. So the energy is to do with the full range of motion, if you like, of the wave. So the formula, the mathematical formula between them is not just k times a, it's k times a squared, because it's more than just one amplitude. It's the amplitude up and down. So if it doubles, and then overall the energy quadruples. So it's E equals ka squared. Now the problem is k is a proportional, constant proportionality for lots of different waves. You don't know what that k is until you do some experimental work with it. There's no set k value. However, you know the k is going to be constant for the same wave. So for the same wave, you can have E1 over A1 squared is equal to E2 over A2 squared. So if for the same wave, energy changes, then you know what the amplitude change is going to be. It's a bit like when you do irradiance or momentum or something higher. You know what E1 and A1 are, you know what say E2 or A2 are, and you can work out the fourth one. So some questions in that in your tutorials as well. The third part here is something about what's known as a travelling wave. So when we did simple harmonic motion, we represented a wave just oscillating about a single point. A pendulum oscillates about a single point, or a spring oscillating about a single point. If you think about something just oscillating up and down, just like a bouncing spring, it goes up and down. So waves that oscillate as well as travelling forward is known as travelling waves. So we have the bit that's going I'll go this way. You have your wave oscillating up and down, simple harmonic motion formula, but they also move forward. So not only are they going up and down, but it's also going forward. So you get this motion here. So you think about a point on the wave, it's going up and down and also moving forward. So a travelling wave has a horizontal distance travelled and a phase separation from its original starting position. So if you think about the starting position is here, and as the wave moves forward, it is a phase separation from here to whatever it is. And it also has its distance travelled. The formula for the position of a point on a travelling wave can be considered the same as a simple harmonic motion formula, with an additional phase separation subtracted. That's that symbol there, I'm going to call it capital theta. So simple harmonic motion is a sine omega t. The omega can be changed into 2 pi f, so a sine 2 pi ft, and then we subtract this, travelling wave equation subtracts this phase difference here from the last slide. So y equals a sine 2 pi ft minus the 2 pi x over theta over lambda. 2 pi comes out and you get your formula here, where x is a horizontal distance from the origin, just like we did in a couple of slides ago. But also, because t is 1 over f, period is 1 over frequency, v equals f lambda, you can substitute these back into this formula and get these two formulas as well. You're given this in the formula sheet, you're not given these, you're expected to be able to put them in if you need to. So if you're asked a question in the tutorial that gives you period, say, and wavelength and time, but doesn't give you some of these, you can put that in there. Right, nice short one this week. This is the last slide. Goes on to stationary waves. Again, stationary waves can be found on, I'll just check the textbook here. They're actually on page 78. I'll add that to the slides. They're on page 78. Now, stationary waves, you just need to be familiar with what they are and how we use them to get data. So we've got a stationary wave are produced when a reflected travelling wave overlaps the original travelling wave and produces a waveform that looks stationary. So a wave goes forward, reflects, and then bounces back. And what happens is you get these stationary points. If you watch the video animation about with the electric toothbrush, which is attached to the assignment, you see the wave vibrating up and down. And you get these points where it looks like the wave's not moving. So what's happening is the wave is going forward, but reflecting off a surface and reflecting back again, and you get these bits where our maximum amplitude are bouncing up and down, and bits where you get nothing happening. These are called antinodes, and these points here are called nodes. So superposition is them basically interfering with one another and overlapping one another. Stationary waves can only be produced with specific distances between the source and reflecting surface. So if you change this distance here, it doesn't quite work. You have to just vary the distance, or you can change the frequency of the wave and also get a standing wave. Parts of a stationary wave are referred to as nodes and antinodes, just like I've explained. And the distance between nodes on a stationary wave is half a wavelength. So the distance between these two nodes is half a wavelength. And the distance between nodes can be counted to get wavelength. This can be used to get frequency and wave speed. So there's a wee bit of that in your tutorial as well to get that working. So that's us this week. There's not a lot in it this week. Please read the textbook, get all the extra details, watch the extra videos, and join me on Thursday for your live session, and we can ask any questions, about tutorial questions, etc. There'll also be a check test this week on this, and you're probably going to get a wee bit longer this time to finish all that. I'll give you the week after to catch up because it is a holiday week. Okay, any questions as usual, get in touch, and use the chat function in the team as well to ask any questions. Good luck.